Welcome you all. Now let us see the concept of mathematical modeling. Overview of this session is technique of mathematical modeling, types of models, uses of mathematical model. First, let us see the concept of mathematical modeling. Mathematical modeling consists of the translating the real world problem to mathematical problem. Then we have to solve the mathematical problem using some mathematical techniques. Then we have to interpret these mathematical solutions in the language of the real world problem. Now, for example, let us consider to find the height of a tower without climbing it, to find the width of the river without crossing it, find the temperature at the surface of the sun without using thermometer there, to find the mass of the earth without using a balance, estimate the population for the particular year, to find the volume of your blood in the human body. So, we have to all these problems and thousands of similar problems can be solved through mathematical modeling. So, we use the mathematical relations developed to solve for the entities which cannot be measured directly in terms of those entities whose values cannot be measured or known. So the mathematical relations we get maybe in terms of algebraic equations, transcendental equations, differential equations, difference equations, integral equations, integral differential equations, differential difference equations, or even in terms of inequalities. So we try to express the height of a tower in terms of some distances and angles which can be measured on the ground. For the second one, we try to express the width of the river in terms of some distances and angles which can be measured in our side of the river. For the third one, we try to express the temperatures at the surface and the center of the sun in terms of the properties of light received from its surface. Then for the fourth one, we try to express the mass of the earth in terms of known masses and distances. Types of models: statics or dynamics, discrete or continuous, deterministic or probabilistic, linear or non-linear, explicit or implicit, qualitative and quantitative. Uses of mathematical model: natural sciences such as physics, biology, earth science and chemistry. In engineering disciplines, computer science and electrical engineering. Non-physical systems such as social sciences, those are economics, psychology, sociology and political science. Mathematical models are also used in music, linguistic, philosophy, for example, intensively in analytic philosophy. Some areas where mathematical models are highly used are space technology, manufacturing and design. Second one, seismology, environment, economics, material research, water resource, drug design, population dynamics, combat and war related problems, medicine. As an illustration, let us consider the diffusion of glucose or a medicine in the bloodstream. So here we have to find the volume of blood in the human body when glucose or some medicine is injected in the bloodstream. For this one, here let us consider V be the volume of blood in the human body and C of 0 denotes the initial concentration of glucose in the bloodstream, and let glucose be introduced in the bloodstream at a constant rate capital I. Glucose is also removed from the bloodstream due to physiological needs of the human body at a rate proportional to C of t. Then using continuity principle, we get the differential equation as V into d by dt of C of t equal to I minus Kc. Let a dose D of a medicine be given to a patient at a regular intervals of duration capital T each, the medicine also disappears from the system at a rate proportional to C of T. And here C of T denotes the concentration of medicine in the bloodstream. Then the differential equation given by the continuity principle is V into d by dt of C of T equal to minus K into C of T. Integrating this differential equation, then we get the solution of C of T. That is, the concentration of glucose at the time T is nothing but C of T equal to D into e power minus K by V into small t. And here small t lies between 0 to capital T. At time capital T, the residue of the first dose is D into e power minus K by V into T, and another dose capital D is given, so that we get C of T equal to D into e power minus K by V into capital T plus D into e power minus K by V into small t minus capital T. And again this can be written as using simplification D into e power minus K by V into T plus D into e power minus K by V into small t minus capital T, and here small t lies between the interval capital T to capital T. The first term gives the residual of the first dose and the second term gives the residual of the second dose. Proceeding in the same way, we get after n doses, and the concentration of glucose can be taken as C of T equal to D into e power minus K by V into small t plus D into e power minus K by V into small t minus capital T plus D into e power minus K by V into small t minus 2 capital T plus etc. plus D into e power minus K by V into T minus n minus 1 into capital T. Again, this can be written as, here we have to take D into e power minus K by V into T outside. We get D into e power minus K by V into small t into 1 plus e power K by V into capital T plus e power 2k by V into capital T plus etc. plus e power n minus 1 into k by V into capital T. Again, this can be written as D into e power minus k by V into small t into e power n into k by V into t minus 1 divided by e power k by V into t minus 1. Here small t lies between n minus 1 into t to nt. Then C of nt minus 0 can be written as D into 1 minus e power minus k by v into nt divided by e power kt by v minus 1, and C of nt plus 0 can be written as D into e power kt by v minus e power minus k by v into nt divided by e power kt by v minus 1. And here C of nt minus 0 and C of nt plus 0 represents the concentration of glucose at the beginning of the interval and ending at the interval. The concentration never exceeds D by e power 1 minus e power minus kt by v. The graph of C of t is given in the following figure. From the above figure, we observe that in each interval, concentration decreases. In any interval, the concentration is maximum at the beginning of this interval, and this maximum concentration at the beginning of an interval goes on increasing as the number of intervals increases. But the maximum value is always below d by 1 e power kt by v minus 1. The minimum value in an interval occurs at the end of each interval. This also increases, but it lies below d by e power kt by v minus 1. The concentration curve is piecewise continuous and has points of discontinuity at capital T, 2t, 3t, etc. By injecting glucose or penicillin in blood and fitting the curve C of t equal to d into e power minus k by v into t, and here t lies between 0 to capital T. To the data, we can estimate the value of k and v. In particular, this gives a method for finding the volume of blood in the human body, and here v is the volume of blood in the human body. Let me conclude this session by importance of mathematical modeling. Modeling makes an important contribution in terms of developing problem-solving skills of students. Also, modeling emphasizes mathematical relations and ensure for students to develop their learning styles and understanding of mathematics. So, modeling is very essential for our day-to-day life. Thank you.